on to area. Sounds real easy, and in a lot of ways it is. So like a lot of the area you guys would have done probably in junior high, like area of a rectangle is length times width. Yeah, we're still doing that. Okay, area of a triangle, still doing that. So now obviously it is calculus, so we will take it up a notch, but you'll still do some of the things. But something we got to talk about before we get into area is sigma notation. Okay, the sigma is that Greek symbol. It kind of looks like an E, for lack of a better word, that little squiggly E. All right, if any of you end up going Greek when you're in college, some of you might have sigma in your Greek title that you're part of. And what it is it's if you had a sequence of numbers, it's you're adding that sequence up. That's all it's doing is a sum. So if I were doing a sequence of even numbers, I would be adding 2, 4, 6. I could put a sigma in front of it and denote even numbers. And so it's written like this. Your starting value is this number on the bottom. And then you'll go up to n, whatever that value is here. Okay, so if you notice, I have my first term, my second term, my third term, my dot, 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 all the way to the nth term. Okay, so that's where that's coming from. All right, so we're not going that way, this way. So we're going to practice writing sums and evaluating sums. So on the first one, that is saying I'm starting at 1, and essentially you're plugging them in here. Okay, so I will plug in 1 plus plug in 2 plus plug in 3 plus plug in 4 all the way up to 6, but it's just a linear term. We're not multiplying by anything. We're not adding anything in that individual thing. So we're actually just adding up whole numbers between 1 and 6. And so then I can evaluate that sum, and 1 plus 2 is 3, and then we'll have 6, 10, 21. And so that is that sum. Okay. All right. Some of them we'll find and some of them we'll just write out for. So some of them are a little wonkier than what you would actually evaluate for. So this one, we will plug in 0 plus plug in 1 plus plug in 2 all the way up to 5. So we'll do 0 plus 1 plus 1 plus 1 plus 2 plus 1, 3 plus 1 plus 4 plus 1. Oh, I lost my plus sign, 5 plus 1. So you would have this, which is actually 1 plus 2 plus 3 plus 4 plus 5 plus 6, which is going to be 21 as well. Okay, so it actually ends up being the same summation. So you might realize sometimes you might be able to adjust your limits or your interval that you're doing it on to make it easier for certain formulas. So it may start at 0, but I can maybe tweak it to make it start at 1. Because I'm going to give you some summation formulas for really, really big ones, so you don't have to write all these out. All right. Let's just plug them in. We don't have to actually evaluate it. So pay attention to the directions on your homework. It may say just write out the sum, or it may say evaluate the sum. It says evaluate it once in a value answer. So now I'm going to plug in. We'll do 3 squared plus 4 squared plus 5 squared. 6 squared plus 7 squared. And then if it asked you to evaluate, you would actually just go and square those and add them up. Okay. Any questions on that? Okay. So then, seems redundant, but it's still good practice. We'll do 1 over root 1. Notice we changed letters from I to J. We got a K. They can pick any letter really they want. But I, J, and K are probably the most common ones. Well, I'm writing things that I'm not meaning to. So then this one's a little different. So if you notice, I have 1 over n. Okay. And n is that top number. Okay, so I don't know that number. I just know it's that top number. So that would be the equivalent of me going from 1 to 5, and then I have 1/5 k squared plus 1. That doesn't mean every time I do one, I'm not plugging in a different number for n. N is a constant number. I just don't know what it is. So when you write out this sequence, you're going to have still 1 over n every single time, but I will plug in for k. So pay attention to the value you're plugging in for, because you might have other unknowns as part of your sum. So then what happens then if I'm writing a sum like this, oops, I left that off, but I don't actually know where it ends, you will do, what do they call that in English? An ellipses? You'll do a dot, dot, dot. That's what I call it. And you're leaving that space in there for when I get to 1 over n squared plus 1. You could even have a term before that that said 1 over n times in parentheses, n minus 1 squared plus 1. Because that would be the term before n. Okay, you just don't know what it is. But you can write it like that. So then taking it up a notch on the next one, it's in function notation. So that we don't know what the function is. So before that we had, our function was like an x plus 1. Our function was x squared. Our function was 1 over root x, that kind of thing. This one, we don't know what it is, but we can still add them up. So we can have f over x sub 1, meaning I'm plugging in my first term, delta x, plus f of x sub 2, delta x, plus dot, 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 dot. We're going all the way to n. I would like to do an n minus 1 term. So I'm going to do f of x sub n minus 1. That is right before the last term, because the last term goes to n. F of x sub n. So you're still doing the same thing, even though you have no clue what this function is. So, I mean, if we went to 3, we would just only go to 3. But if we were going big, you would use this. Any questions on just what it means to write a sum? And if you have enough information, you could evaluate them. On those last ones, we don't have enough information. But
wait, why are you writing an n minus 1?
That is the term before n.
Oh.
That's it.
Oh,
you don't technically have to write it. So I could have written in here. I could have also written a term like that here, but you'd have to be really careful. But it's just, and you could do n minus 2. I mean, you could really, have you guys ever worked with the Fibonacci sequence at all? When you do Fibonacci, it uses like a recursive, it uses the term before. And so they use that n minus 1 and n all the time. So the next number in the Fibonacci is the previous 2 numbers before. So when I write that, it's like, oh, my new number is n minus 1 plus n minus 2. It's the 2 previous terms. So, fun, very fun stuff. All right. I want to make sure we have it all written down before I roll on. Okay. Oh, too far. Okay, so summation formulas. I am telling you this. Obviously, your tests for now are online, but someday they won't be, and you may not always have your formulas with you. And if you take calculus in college, like, you have to memorize these at some level, okay, these summation formulas. So what they are is, instead of, say I was doing a sum from 1 to 100, instead of doing 1 plus 2 plus 3 all the way to 100 and then typing that in my calculator or trying to add in my head, I just plug it into this formula, and that's it. It makes it so much easier. So, for example, on the first one, that's a constant. So if I'm doing from 1 to 1,000,000, the sum of 2, it's just 2 times 1,000,000. So 2 million, that's the sum. And think about it, if I was doing something easy. So 1 to 5 of just 2. Well, 2 plus 2 plus 2 plus 2 plus 2, if I have 5 of them, that is the same as 5 times 2. Okay, so that's a simpler version of that. So you don't have to actually go and add a whole bunch of things. You can just plug it into the formula. So then 2 would be easy. So that one we just did, that was 1 plus 2 all the way to 6, I could have just plugged in 6 and still got 21. Because look at plugging in 6 here. I will have 6 times 7, which is 42, divided by 2, which is also 21. So I didn't even have to go and add those up, which is not bad to do 1 to 6. But again, if I asked you to do 1 to 100, I would much rather plug in 100. Okay. So these are the 4 most common ones. There is one for I to the 4th. It's not terrible. It's really not. But these are the 4 main ones that you're going to do. And then I squared, you plug in here. And it shows you where to plug in your n. So if I'm doing, again, 1 to 6 of I squared, then I just go put in 6. So I'll do 6 times 7 times 13 divided by 6. And then 4, I think, is easy to memorize, because if you notice, 4 and 2, 4 is just 2 squared, entirely, top and bottom squared. Okay, so that's how I memorize that one. If I'm doing I cubed, it's going to be the ith formula squared. All right, so those formulas are important, and we'll see how they work. All right, so we are evaluating the sum from 1 to n of I plus 1 over n squared for 10, 100, 1,000, and then 10,000. So plugging in 10, it wouldn't have been that bad, but even to 100, we don't want to do that by hand. So what we can do is we can use the sum formula and create a general formula for the situation. Then we can just plug in 10, plug in 100, plug in 1,000, plug in 10,000, and it's so much easier than that. So what we're going to do is we're going to take this formula that they gave us, and we are going to use the summation formulas to come up with a specific formula for this instance. So what I want to do first, you see how it's divided by n squared? N squared is just a number. It has nothing to do with from what to what, okay? It'll be very specific to each instant. I'm going to factor that 1 over n squared. I'm going to factor it out as 1 over n squared. And so instead of dividing by n squared, I have 1 over n squared times that whole thing. So I'm going to rewrite this first. That's how I do my sums, by the way, real fancy. I just do a sharp E looking thing. If you want to write them a little neater, go for it. So I have this, and then now, since I factored that out, all that's left is this. And I'm going to put it in parentheses to make sure we add the whole thing. Okay, so I have this. What's great, though, is if you scroll back, I have a summation formula for just I, and I have a summation formula for a constant. Okay, so I will rewrite this as 1 over n squared. In place of that I am going to go plug in this formula here. Okay, so in place of that I am going to have n plus 1 all over 2. Okay, so that is just for I. Well, then in place of 1, if I go look at my formulas, for a constant, it's just c times n. My constant in this case is 1, so it's just going to be 1 times n. So it's just n. So I have this. Okay, so that would be my summation formula. Sometimes they'll ask you to write a formula for the situation using the summation formulas. So you would simplify this, combine like terms, make it one fraction, and then you would go plug in your numbers. And we're going to do that because you will have some homework problems and we should practice it. So what I would do now is let's factor out an n. Do you see the n on this term and this term? That they both have one? If I factor that out, I will have n over n squared times n plus 1 over 2 plus just 1. Do you see that? Factored an n out of each one. Okay. So then that makes this nice to where I just have 1 over n. Then I need a common denominator, which is not too bad because my denominator is currently 2. So if I make 1 a fraction with a denominator of 2, what will that be? So then I can just add, and I will have 1 over n outside, and then I'll have n plus 3 over 2. And if you want, you could write it like that, or you could write it like this. It's whatever's easier for you to plug into, really. It wouldn't matter. So that's the summation formula. So now, if I do the sum, I equals 1 to 10 of this whole thing, I will just do 10 plus 3 over 2 times 10. I'm just going to plug in 10. So you do a lot of the work up front, so you don't have to do it throughout. Okay. So we'll have 13 over 20. So if you wrote it as a decimal, it's exactly that. So then for n equals 100, we would have 100 plus 3 over 2 times 100. So we have 103 over 200, or 0.515. So for n equals 1,000, we'd have 1,003 over 2,000. which is, making sure I'm doing this right. And then last one is 10,000. And you would have 1,000, 10,003 divided by 20,000. Okay. So it's still a lot of work. It's just better than doing plug-in 1 plus plug-in 2 plus plug-in 3 plus plug-in 4 all the way to even 10 would be annoying. But 10 would be doable, 100 would be irritating. And imagine all the errors you could make plugging that in. Okay, any questions on that process? Okay, you understand how we got from here to here? Plugging in? Yes.
Okay, so on all of the formulas,
Mhm.
it has I equals 1. Is that super important?
It's super important. So when I was saying you can tweak things, potentially what you could do is you have to make sure algebraically it's not going to affect your answer. But on that previous one, if we go, don't make you guys dizzy. But if I were given, say, what B is, that plus 1 would make it exactly what it was before. So I could take away that plus 1 and put that plus 1 back in the expression and move everything up 1. Now, depending on fractions and stuff like that, you have to be really careful. But like a solid number of just I, then I could just shift it up by that much, okay, or take it down by that much. So say if I had from like, I don't know, 2 to 7 on A, I could do I minus 1 and take it from 1 to 6. But it needs to be 1. They will on the AP test, they're going to give you 1, unless they just want you to evaluate it basically like it's not huge. But if they want you to use the summation formula, they will start you at 1. For the most part. Or it'll be simple by like adding or subtracting. Okay, so yep, we did that. So sorry, this is curvy. So summations are used in finding area. So this is tying it together because we're going to approximate area under a curve. So in geometry, we do areas of very specific shapes that don't have a lot of variation, like a circle or a square, and it's very consistent all the way around. So like a circle, obviously it has a continuous radius throughout. These are more like sections of a curve that you can't use any of those geometric formulas. I mean, if you get at something that makes a triangle, by all means, just do 1/2 base times height. But in this case, it's not a circle, it's not a semicircle, it's not any of that. We can approximate the area by using rectangles, something we know. And so what they do is they're breaking it down consistently into a certain number of rectangles. So if you look at A, the rectangles are all underneath the curve. Okay, that is called inscribed figures because they're inside. And then if you look at part B, they're outside the figure, and those will be circumscribed rectangles. So they might ask you, evaluate or approximate this area by using inscribed versus circumscribed rectangles kind of thing. They may not tell you how many, they may tell you and not give you a picture. They might say by using 5 rectangles of equal width. And so then you'd have to go and say, oh, well, my interval is 5. So each one has a width of 1 and go in and draw your rectangles. And they may do things like that. So in this case, they've given us rectangles. We're going to do 2. They've given us 5 rectangles, and we're going to find both approximations of the area between the curve, which they gave us, x squared, negative x squared plus 5. And then they gave us an axis. Its x-axis is bounding it, and the x value of 0 and 2. Okay, so they cut off the rest of the graph. We're zoomed in at just between 0 and 2 and the x-axis. Okay, that is something we could have drawn. We didn't need them to draw it for us. We could have drawn it ourselves. Okay, we would have drawn the whole graph, and then I would have zoomed in on between 0 and 2. The 5 intervals, if I'm going between 0 and 2, okay, I'm going to zoom in on this. Kind of blurry. But if I'm going between 0 and 2, I need to split it equally 5 ways. So if you notice, we divided everything by 5. So 10 divided by 5 gives me my 2. I've got to split it equally 5 ways. So then I have 8/5, 6/5, 4/5, and 2/5. Okay, to make them all split into equal parts. Okay, is what we would have. All right, so we will use that in area. So I'm going to zoom back out. So I'm going to call these, for part A, rectangle 1, rectangle 2, rectangle 3, rectangle 4, and rectangle 5. And so we will do a sum for these. You could write a summation for these, but we're going to just sum up the 5 rectangles. So let's find the area of rectangle 1. We're finding area. I'm just going to write area for rectangle 1, rectangle 2, rectangle 3, rectangle 4, and rectangle 5. Okay, and this is part A. So area is a rectangle's length times width. Okay, if you look at all the widths, though, they're all exactly 2/5. I go from 2/5, add 2/5, I get my 4/5, add 2/5, I get my 6/5. So each of these have a width of 2/5. Every single one of them has that. Okay, all of them do. So for all of them, that length is 2/5, or width, or whatever you're gonna call it. I guess width. Or base. How about base times height? I like that better. But then we're going to have to multiply. I'm going to write a note here, base times height for our rectangle area. But we're going to have to multiply them by the height. And that is not something that's consistent. If you notice, the bases are all consistently. They're equally spread apart. The heights vary. I mean, you can look at the gaps of the curve and that some are bigger than others. Okay, the height is not consistent at all. So we have to figure out, how am I going to obtain the height of this first rectangle? Well, think height like y value, think up and down. Okay, if we were to rotate the opposite direction, you would think of height as more of a x value. It would not be as consistent. But how do I get that y value? Well, that y value is going to be 2/5 plugged into my equation. Okay, the height of that rectangle is 2/5 plugged in there. Okay, so we will do negative 2/5 in parentheses squared. The negative is not squared, the negative is outside of it, plus 5. And that is going to be the height of rectangle 1. Now, pay attention because it's going to matter. Do you see how I use the point on the rectangle on the curve, and it's on the right of that figure? Okay. If you look straight below the height of this one, I will use the point on the left. There are such things as right and left sums, no matter whether it's inscribed or circumscribed. It could be a combo where you'll use only the left points or only the right points. If they say inscribed, you'll use whatever makes it inside. You'll use circumscribed, use whatever makes it outside. Okay, so that right one is making it inside. So that's why I chose the right one. Okay. We can go ahead and fill this out for the rest of these, and then we'll evaluate. So then I'll do negative, and the height for this one comes from that point, which is 2/5 to the right of 2/5, which is 4/5. So I'll plug in 4/5. And then I'll plug in 6/5, which will be the next one. Because the right point makes all these inside. It's not just because it's on the right. It's because it makes it inside. So if you look, that first one is going to be an underestimation, and the second one we do is going to be an overestimation because it's hanging outside the curve. So go ahead and we'll write all these. You can see those on the graph, but those are things we could have come up with our own. I'm going to write 10/5 as 2 because it is 2. I'm going to write it as 10/5. Okay, before we evaluate each of those, I want to make sure you guys are with me on why we chose those points, why we're plugging them in, where we're plugging them in. Okay, so if we were to get those, you can use your calculator, and you have to just be very careful to make sure you square that correctly. Plus, you get a common denominator, things like that. I have already done them, so for the saving of time, I'm going to assume you can use your calculator correctly. Okay, just make sure the parentheses are where they are. That's important. Okay, so if I do this, I'm going to have 218. Nope, I lie. That's the one below it. 242 over 125. We're going to have 218 over 125. And there's a reason I'm not rounding, because it's already an approximation. You don't want to round before you round your approximation, because then your approximation's way off. And you only have a few decimal points of forgiveness on the AP test. One of the reasons we go to 5 decimal places is they grade accuracy to 5 or to 3. So if we go 5, then we definitely are containing hopefully the right 3 that they need. And then the last one is just 2/5. So then you would add all those up. I like to write it like this. Kind of like you're in junior high and you add just straight down, and you're adding all those up. And that's going to be your area approximation. So area is approximately, I'm going to use an approximation symbol, 162 over 25 which is 6.48. We don't have units or situations, so we'll just call it units squared. So that's an underestimation for this curve. So now we're going to overestimate this curve. And I'm going to zoom out a little bit because I want to keep the numbers I have currently, because if you notice, some of our points will overlap. Well, I've already done the work for it. You don't want to lose that work. So I'm going to call this rectangle 1, this rectangle 2, rectangle 3, rectangle 4, and rectangle 5. Okay. And then we are going to find each of those areas carefully. Okay. And this will be our last problem for today. And then we'll finish up tomorrow. Okay, so for part B, we're still doing area. So rectangle 1, if you notice rectangle 1's height, the widths are still the same. They're all still 2/5. But this one's height comes from plugging in what number? 0. So I'm going to have negative 0 squared plus 5. So that'll be easy to do. We'll worry about it later, though. And then R2 is going to come from this height, which is plugging in 2/5, right? Which I already did. We already know that that is 242 over 125. We did that work here when we plugged in 2/5 before. Okay, so sometimes they'll couple these problems together. Don't overwork yourself. It's not going to hurt you to check yourself, but I mean, it's going to be matching. All right, so then this one's height comes from plugging in 4/5. Which I know is 218 over 125. And then our fourth triangle comes from plugging in 6/5. Which is 178 over 125. And then our last rectangle comes from plugging in 8/5. So we don't make it to the 2 or the 10/5, which is 2. Because we don't need that one to determine the height. But all these left points, these left endpoints, they make it hang over the edge of it.
I remember last time I took the SAT, I think there was a problem like this.
Summation, probably. Summation, we have done zero calculus at this point. Yeah, this is all algebra.
I had this on some other homework a long time ago.
Yes.
And I was confused on it
Yeah.
then.
Summation is considered like a algebra 2 concept. It's just a matter of, it's usually the last chapter, like in the textbook. And if you get there, great. And if you don't, bummer. Like, it's just not going to be there. So, okay. So then we just need to evaluate 5 times 2/5 is leaving us with just 2. So we'll add all these up. Oh, I thought I meant to erase that. And when we add all these up, we're going to get 202 over 25. So our area is approximately this, which is equal to 8.08. So the actual area is somewhere between 6.48 and 8.08. The more rectangles you have, the more accurate your area is going to be. Okay. If you had infinitely many rectangles, you would be exactly correct on the area. So I say that because I'm leaving you on a hanger there. We'll go somewhere where we do actually infinitely many rectangles. Obviously, you don't have to draw them. I would like to see you try. Yes, JJ.
Is it safe to assume it's pretty close to the middle of those two?
If you average them, you're going to be even closer. Okay, but it might not be, because you look sometimes. I mean, what hangs out is not necessarily what's hanging in. So, but you'll be even closer, yes, if you average them. So we'll do tomorrow some midpoint where you don't go left or right. You actually go in the middle of each interval. So we would have used 1/5, 3/5, 5/5, that. And those are even more accurate because you have equally hanging in, equally, I say that loosely, that's not correct. You have some hanging in and some hanging out.
Oh, that's kind of.
Yes. And so that's going to be even more accurate, but they're all still approximations because you would have to have infinitely many of them to be perfect.